All right, we are going to be looking at today a prototype, just a shell and tube heat exchanger. So in the chemical plant, like we mentioned, we often need this process fluid to be at a certain set point, a certain temperature and pressure. And so we'll pass it through a heat exchanger. And we can represent the heat exchanger as something like this, where we have a shell that sits around a pipe. So we call this the shell and tube heat exchanger. And so we have the shell side and the tube side. And in this case, let's consider a process fluid that we're trying to heat up. So in this case, in the tube, what we'll have is we'll have a cold fluid coming in. So we'll call this TCI, as this cold process fluid is coming in, and then the whole goal is to get this process fluid to warm up by the time it leaves this heat exchanger. So we'll still call this TC, but we'll say it's the cold fluid outlet temperature. We generally neglect the pressure drop in pipes in the tube side of the shell and tube heat exchanger. Generally, we say that delta P is 0. Otherwise, we need to include more terms in our enthalpy change. But we assume delta P is 0. And so on the hot side, then, we could either inlet the hot fluid here or inlet the hot fluid here, keeping in mind that our cold fluid is moving this way. So first, let's set up a situation where we have what we call a parallel flow. So if we inlet the hot fluid here, then the hot fluid will generally be moving parallel to the cold fluid. And we could have the hot outlet temperature is going to be something cooler than the very hot inlet temperature. And if we plot this spatially, so we'll look at both the hot process fluid and the cold process fluid as it's moving through here spatially. And I think I can move this thing down. Good. Move that bubble. We can plot then the hot fluid starts at some very hot inlet temperature. And then that's going to cool down as it's passing through this system. The cold fluid is going to start at some very cold temperature, and that's going to warm up. And of course, we'll never, ever, ever get the cold temperature to exceed the hot temperature. The best we can do is if we make this infinitely long, is that we'll come to some equilibrium where everything reaches some medium temperature. But in reality, this is what we'll have if we have a parallel flow heat exchanger, is the hot fluid will cool down in a logarithmic scale, and the cold fluid will heat up in a logarithmic scale. If we reverse this, so we still have keep cold flowing in the same direction. But now we want to take our hot fluid and inlet it counter flowing is what we say. So now we have a counterflow heat exchanger where the flows are opposing one another. And if we plot this spatially, as we pass through this heat exchanger, what we'll find is that the cold fluid still should be warming up. But we'll find the hot fluid is over here, and that cools down as we move through the heat exchanger. And so this delta is actually much more favorable than this delta, because the Q is proportional to this area. So if we have a very large difference between the cold stream and the hot stream, Q is very large. By the time we've reached the outlet of this heat exchanger, Q of X is very small. This is becoming less and less efficient the longer we make it. That's not really desirable as an engineer trying to design something. Here now, if we look at the heat transfer and the driving force for that heat transfer, right? We always craft things in the context of driving force and resistance. I can keep increasing the length of this, and this area is relatively constant. Q1, Q2, Q of X, it's relatively constant. And so generally, you will choose to set up heat exchangers or mass exchangers, right? You could have what we call a plug flow reactor as a counterflow situation. I guess that might not make sense as a plug flow reactor, but if you do have the opportunity to have the species, say in counterflow, you would choose to do that.